Okay, so let's go back to the question once again, and we're going to go through the design procedure, and we're going to do it according to, with some extension, according to the procedure that we explained in the part one of this video. So now, once again, we have the driver given as a gasoline engine. The driven is going to be heavily loaded coal conveyor. The RPM value or the omega for the input is going to be 94.23 radian per second at 11.8 kilowatt. And for the output, it should be designed to be anything between 24 up to 25.12 radian per second. Again, these units can be changed directly to IP units, like the 94 multiplied by 30 divided by pi will give you the RPM. The 11.18 can be divided by 0.75 to give you the horsepower. And the same thing is going to be for the range for the output. Now we need to find a design for the chain drive. So the first step is this is the given value. And we need to get what the design of the chain drive. We are not going to use the 11.18. We need to choose for a higher value, which would be the design power. To find the design power, we should need to find the factor, the overload factor. So we start with the calculation. First, we're going to go to the step to find the design power. So specify the service factor and compute the design power. And that's what we can do from the table 717. So we go to the 717 and we're going to choose what we have. So first we have the critical motor or turbine. No, we have internal combustion engine because it's given to us as a diesel engine. So that will be the engine we're looking at. Now let's look about what is the load time. Smooth, give you here what's actually the type of the smooth loads. We have moderate shock, pocket elevator, machine tools, cranes, heavy conveyors. Okay, and continue with that. So mainly we have the heavy conveyor. I don't want to go to the last one, which is going to be punch press, the hammer mills, and both propellers. So yeah, we have the heavy chains, heavy conveyors. So again, to choose the moderate shock against the internal combustion engine, and this will give me that the value for the design factor is going to be 1.4. Now that's it. I am going to do the calculation for the design power, and this will be equal to the input power, which is a 11.8, I think. Yeah, 11.18 multiplied by 1.4, and this will give me that the value to be 15.66 kilowatt. Divide that by 0.75 is going to be 21 horsepower. That's it. Yeah. The other good thing that we have the omegas. Okay, we have the in and the out, so we can calculate the velocity ratio from that, the input to the output. So you remember that we have range of the RPM, so I can choose the average one and do the calculation. So the input is 94 and the output was anything between 24 to 25 point something. So I can get the average and I will get 24.6 for the NO. So I'm going to put that in the equation, and the velocity ratio or the speed ratio, whatever you call it, is going to be equal to 3.83. Remember that as what we have in the gears and as what we have for the belts, the NI multiplied by the number of the teeth for the input is equal to the RPM value for the output multiplied by the number of the teeth for the output. So later, we can find out what will be the number of the teeth for the output sprocket by having this ratio. Now we need to choose the plane page value, and this can be done by using any of the table 1714 to 1716, the one we talked about, the type 40, the type 60, and the type 80. So we come first to find what is the RPM value for the sprocket and the input, and what is the power for the input. So you will know that 94.23 multiplied by pi, 30 divided by pi, will give you the value for the RPM. So it's going to be 900 RPM. For the horsepower, we said it's going to be equal to 21 horsepower. Now we're going to choose according to the tables, the type 60, because that's what we're going to find as the most suitable horsepower at this RPM. And I will show you that very soon. So now we're going to check the table 716 on the next page. We're going to use one strand only. Okay, and that's the table 715 for the type 60, which is going to have the pitch value of 700.75 inches. So we don't have 900, so we're going to choose in between 800 to 1000, and we get to the 21, which is going to be between those and between those. Okay, so that will be the one that I'm looking at. It's can be between 19 and the 21, but in my solution, I choose the 18. The book choose 17. In the end, we're going to get similar answers. So that's the point we're looking at. Looking at 900 and the power between 20.77 to 26.73. I need to have the 21. So I need for the interpolation here to find the rated power. And we can find that actually 900. We can choose that. So anyway, I choose the 18 teeth for that. Sometimes the interpolation is going to be an extra step. I don't want you actually to suffer from that. So we got the number of the teeth to be 18. I'm going to use according to that. Now the pitch value, as we said, is going to be 0.75 in inches. You can find it in millimeters. And we're going to use the type B with the path or the disc lubrication process. Now, once again, according to table 715, number 60 chain, single strand chosen, the operating on the 18 teeth sprocket at 900 RPM. The rated power is going to be 21.69. Type B loop path should be used. Now, we're going to have another step. We need to calculate the number of the teeth for the larger sprocket. We can say that, okay, now we got the smallest sprocket, 18, and we have the 3.83 as the velocity ratio. So now I can calculate the required number of the teeth at the larger sprocket. So the 18 is sitting there as a number. We're going to use the 18. The p-value is 19.05, which is the 0.75 inches multiplied by 25.4. I don't know why this one is overlapping. I'll try to fix it. Now we can find the number of the output teeth. We know the input is 18. We know the 3.83 is the velocity ratio. And this will give me that the number of the teeth and the output is going to be 68.94. Definitely, I cannot choose the 68.94, so I can choose 69. So 69 is going to be the teeth for the output sprocket. Once again, we got the pitch value from here, 63/4, and that's the average tensile strength in pounds. We have the metric table, so you go to the metric table, and again, it's going to be that one. So the metric 60, which is equal to 12B, is going to have 19.05 millimeters for the pitch value. Okay, so now we're going to, and by the way, 28.9 kilonewton for the braking strength. Now we're going to calculate the actual expected speed, because now the number of the teeth has been changed. We did some approximation. So we need to check what will be the new velocity ratio depending on the teeth numbers that we had. So now we had the input teeth is 18, the output teeth is 69. So I can compute for the actual speed ratio. And this will give me 3.83. So it's the same. So then the output speed is going to be equal to the input speed multiplied by the speed ratio. This will give me definitely the value of the 24.32. You remember that I start my design using the 24.6. So yeah, it's within the range. It's more than the 24.1 and less the 25.4. So all good. It's within the range. Now, at the step about the calculating of the pitch diameter or the diameter of each sprockets. So we're going to go once again to the equations equation 720. Now we know the pitch value is 19.05 millimeters, and we know the number of the teeth for the input is 18, and for the output is 69. So we can simply apply the equation for the first part, and we're going to get 109.7 millimeter for the uh, input. For the output, the number of the teeth is going to be 69, so we're going to have the value to be equal to 400.75 millimeters. Okay, now we know the diameters of those sprockets, and now we're going to go to the step of specifying the nominal center distance, C. That's very important because I told you earlier that the less space we're going to have is more efficient design we're going to achieve, because we don't want to have the things to be too large, including that the large thing is going to give me a heavier chain, and this will cause a problem. More vibration, too noisy, and of course going to shorten the life of the machine itself. So we go to the step number 7, which is going to be specifying the normal center distance, and that's where we're going to use anything within the range of 30 to 50 pitches. So we can guess that the distance is going to be 40 pitches for this design. Now with this C value, we're going to design for the length of the pitch, the length in pitches. Okay. So now that's the equation 718. We have the 2 multiplied by the selected C value plus the number of the teeth for the larger one plus the number of the teeth for the smaller one divided by 2 plus the number of the teeth for the larger one minus the number of the teeth for the smaller one squared divided by 4 pi square C. So we're going to put the parameters in. I will come out with the value of 125.14 pitches. Now, of course, I can change that to inches simply by multiplying it by the pitch value, which is 19.05. Okay, so actually, it's going to be nice to show you that. Okay, where's my calculator? Just give me 1 second, guys. So now I can change any pitch's value to an actual length by multiplying by the pitch value we got for the specification. So now we have 125.14, 125.147 multiplied by the pitch value we got is going to be 0.75 inches. So it's going to be 93.86 inches. Multiply that by 25.4. So it's going to be 2,384 millimeters. So that will be the length of the chain. We got the length of the chain. Okay, now let's continue with the rest of the solution. Sorry, I don't know how to get the things open again. I have to close the calculator, close that. Okay, anyway, so yeah, we got the value for the pitches, and we're going to continue with the calculation. We can approximate that, so we're going to get 125 pitches. So we can find the total length or the total pitches we have over the length of the chain, and we can get the length of the chain. And next step is going to be calculating the actual C. We know the L, we know the ends, and then we can put that in the equation 719. And we will come to the value for the actual C value and center distance. And you can actually, there's something very important about the size. You have to be careful about that. You will find that the answer is going to be 38.118 pitches. We calculated 40, so it's going to be okay to leave it like that. Or I can do it as 38 and redesign once again. But anyway, the 38.11 pitches, that means is going to be equal to 25.6 inches if I get to multiply that by the pitch value. And if I get to multiply it by the 19.05, I will get 726 millimeter. That will be the center to center distance, the actual one. Now we're going to use 40 pitches, so the guess was very good. And we're going to go to step number 10, which compute the angles of the room. And we're going to compute the angle of the graph for the chain for each of the sprocket using the equations 721 and 722. Now the same equation, we just need to check for the theta 1, and this should be at least 120 or more. So we're going to put all the parameters in, and we will come out with the value for the theta 1 to be 156.88, which is okay. If not, I said that we're going to suggest a new value for the C and a new value for the L. And of course, this will be something like doing an iteration. Well, it's okay, it's more than 120, so I'm going to calculate the theta 2, which is going to be equal to 203.12 degree. Remember that the theta 1 plus theta 2 should be equal to 360, so check your answer and confirm it. If not, simply you can, when you calculate theta 1, subtract it from 360, and you will get the theta 2. Now, the summary of the design we had is that we're using the number 60 chain with a 3/4 inches pitch value. The length is going to be 125 pitches, which is going to be equal to 2,381.25 millimeters. That's the length of the whole chain. The center distance is going to be the 726.14 millimeter. That's the maximum. Oh, by the way, when you saw the diagram, it was 1,000 something because I choose 18 teeth instead of 17. That's made a difference. The split we're going to use is single strand. The small is going to have 18 teeth, which diameter was 109.7 millimeters. The large is going to have 69 teeth with the pitch value of the pitch diameter of 400.75 millimeters. Okay, so that's the summary of the design, and that's the shape of the design we have. So you can see that I just changed the values because I have a new diameters now and a new length simply by getting that the number of the teeth on the smaller sprocket was chosen as 18, not 17. If you check the book, you will find the other solution, and there's some variation with the answers. Now, the next example, oh, sorry, these are the new values for the angles as well. Sorry, I updated that as well. Okay, now we're going to go now to the second question, and it's going to be just simply redesign the same one, but we're going to have a smaller drive. So this will be covered in the part 3 of this tutorial. Okay.